All right, let's tackle the first part of 14.2, 14.2a. Share my screen with you. Hope you're doing well. All right, so here we have it. Um, Tangent lines to circles. Okay, so um, first thing, obviously, we've talked about this before. We've talked about what a circle is. We've talked about what the circular region is, right? It's the circle and its interior, right? So let's just review that again. So we got our circle, which is the set of points in a plane equidistant from a given point, right, which is obviously the center of the circle. You have the interior, right, which is a set of points with the distance less than the radius, right? Less than the radius would mean you're inside. And exterior would be greater than the radius, distance greater, set of points. Okay. Again, circular region, the circle, and its interior. If I just say circle, I'm just talking about these points. Okay, so what about the points on the circle? Neither the interior nor the exterior. They're on the circle. Okay, so where are the three places that a point can be? You got it, the interior, the exterior, on the circle. Lovely. All right, so a tangent is a line, and oftentimes we'll refer to a tangent and it might be a segment, but it's obviously it's the line that contains that segment. So the tangent is a line which intersects a circle in one and only two, no, I'm kidding, one point. The point is called the point of tangency, or sometimes it's called the point of contact. Okay, so here's a diagram with an example of a tangent. See it right there, and it only hits right there at that red point. I know it looks like it might hit more places, but it's not. Okay, so here we have a theorem that says a line perpendicular to a radius at its outer end is tangent to the circle. Okay, so a line perpendicular to a radius at its outer end, meaning on the circle, is tangent to the circle. Okay, and here is an informal proof hint for you. Okay, what is true about the length of the segment from the center of the circle to any other point besides the point of tangency? What is true about the length of the segment from the center of the circle to any other point besides the point of tangency? It's going to either be in the circle, right? Which means if it was in the circle, the line would intersect the circle in two places, right? It would not be a tangent, it would be a secant. And if it was further, then it's not going to hit the circle at all. Okay. All right. So let's talk about internally versus externally tangent circles, okay? Internally tangent circles are two, or really it could be more circles, tangent to the same line at the same point with centers on the same side of the common tangent. So here's an example, we have two circles, okay? Tangent to the same line at the same point. So it's not like we have one up here and one down here, with centers on the same side of the common tangent, right? Center of the circle there, center of the circle, I don't know about right there, both on the same side of the tangent. Okay. Externally tangent, okay, so again, that was internally tangent. Externally tangent, same point of contact, but circles are on opposite sides, okay? So here, again, same point of contact, same point of tangency, but centers are on opposite sides. Internally tangent circles, externally tangent circles. Okay, now we're just gonna do some practice. Okay, so here you are given two, and I want you to practice these, like try them on your own, okay? Really work on it. I know you can just like let the video play. I'm gonna show you how to do it, but you're gonna learn best by grappling with this, okay? And even if that means struggling with it, that's okay. Okay, so given two concentric circles, which means that they're both technically circle P. We have a little smaller circle P, a bigger circle P, because we usually name circles by their center point. Okay. The radius of the smaller circle is 3, and the radius of the larger is 8. And then we know ST is tangent to the smaller circle at point Q. Okay, and we have to find ST. We're going to find the length of ST. Okay. All right, so mark it up. see what you can do and from what you've learned on the previous pages. All right, so here we go, I'm back. So what we do know is that if you mark this up, let me go ahead and mark it up. The radius to the smaller circle, so like this was 3, right? Should use thinner lines, but and the radius to the larger one is 8. So let's say I just drew this one in here. I could have drawn the other way too, to S. And this is 8, right? And what do we know about right here? What do we know about a radius to a tangent? Aha, we know what? We know that it's perpendicular. We have a right triangle, don't we? So 9 squared plus, well, I did SQ squared, so I did that side, but TQ squared doesn't really make a difference, equals 64. And we end up getting root 55 for SQ, but we know that SQ and TQ are congruent, right? They're the same length because I could have done the 8 over here and it would have been the same right triangle. So it's 2 root 55. Okay, awesome. So that was it on that page. So let's go to the next page. All right, so here you have AB is 8, you have AC is 13, and I'm sorry, AC is 13 and BC is 11. Find each radius. And I'm going to give you a hint. The hint is think about setting up a system. Okay. All right, so I'm going to start uncovering now. So I know that the radius of A, circle A, plus the radius of circle B is equal to 8, right? And then same for these other ones. Well, how could I solve that? I mean, it's a system, right? I can set up a system. I know I could change this one. I could isolate the radius of A. And for this one, I can, for the second one here, the radius of B plus the radius of C equals 11, I can isolate C. And then now notice the radius of A is in terms of the radius of B, and the radius of C is in terms of B. So I can then substitute both of those in for C and for radius of A, right? So it becomes 11 minus RB, the radius of B, plus 8 minus the radius of B, and that equals 13. And then once you do that, you basically, I'm not going to take the time to do it, but you basically could solve, right? That's going to get you radius of B is equal to 3. And then once I know the radius of B is 3, I just plug in and the dominoes start to fall. Awesome. Okay. All right. So here we have a tangent to a radius. Find QM. All right. So I'm back. So it's 6. Right? What do we know? We know we have a right angle there. It's a radius to a tangent, right? So it's a right triangle. And we know if we have a leg of 8 and a hypotenuse of 10, it's going to be a 6, 8, 10 triple. Almost baseball season. Yeah. Okay. This one I love. This is a good proof. Think about how you would solve this and what it would mean if you're proving that proportion that's listed there. Okay, so give it a shot and go ahead and write it out. Okay, I'm back. So if you look at this, what do we have? We have a radius to a tangent here. We have a radius to a tangent here. So these are going to be right angles. And what does triangle PTR and triangle PSQ, what angle do they have in common? Angle P, yes, angle P. So we have what? We can prove those two triangles congruent, or not congruent, similar, obviously, by AA, right? And then if we can do that, then we can set up the proportion using SysTip, right? Corresponding sides and similar triangles are in proportion. All right, and that is it for 12A. All right, we'll get to 12B next. Let me stop the share and say goodbye for now.